Welcome back. In the last one or two classes, we have been discussing about the nomenclature of the coupled spin systems, how to identify them using proper nomenclature. And in the last class particularly, we took example of two coupled spin systems. For example, weakly coupled two spin system which identified as A and X. I clearly mentioned to you, in such a coupled spin system, A will give two lines of equal intensity, X will give two lines of equal intensity. So finally, and you can get the chemical shape from the center of those doublets. Also, this separation, doublet separations, if you measure, you will be getting J coupling. And we extended this logic, when the chemical shape separation became much smaller compared to J coupling, we got a AB pattern. I showed you how the AB pattern was there, wherein two center lines were of equal intensity, which were much intense peaks compared to two lines of outer transitions, which were of very weak intensity. And I also mentioned to you the separation of the two outer lines. Any two outer lines you take on either side, right side or left side, you will get J coupling. And if you want to get the chemical shifts of these, especially strongly coupled, which I identified as AB spin system, I told you it is not possible to get the individual chemical shifts in strongly coupled spins. We can only get the difference in the chemical shifts. So how do you get the chemical shift difference in AB spectrum? I showed you, you have to take the difference of the frequency between the first line and the last line of the four transitions. First transition and fourth transition difference you take. Similarly, take the difference of the second and third, multiply these two factors, take the square root of that, that will give you chemical shift difference between two coupled spins in strongly coupled AB. I also told you how to calculate the intensity ratio. You have to take I2 by I1 is nothing but separation of the outer transitions, the ratio of outer transition, that of the inner transition, which I worked out. I showed you clearly what is going to happen. For example, in a situation like this, I2 by I1, this is a ratio from inner line to the outer line. If you consider, it is a frequency separation between two outer lines divided by frequency separation between two inner lines. This, as I told you, as you keep on increasing this separation becomes smaller and smaller. When this becomes larger and larger, intensity I told you. For example, take, I said, if you take this to be very large value, nu1 minus nu4, and this becomes very, very small, the intensity ratio is very large. That means the internal peak, these two peaks have more intensity than outer peaks. So this all we explained. I also told you root to roof effect, and I said I told about the limiting case when the chemical shifts become same. AX will become AB will become A2. When the chemical shifts overlap, it will become a A2 spin system, and the coupling is not reflected in the spectrum. Now, how we see the transition from AX to AB? This is a very simple example I am showing you. This is a perfect AX spin system. You can see both the lines are of equal intensity. Now, what I am going to do is, the chemical shift separation in this case is sufficiently larger than J coupling. What we will do is, we will try to make it more strongly coupled. How do we do? You keep on reducing the chemical shift separation between these two. This you know how to calculate in the AB. So when you keep reducing the chemical shift separation, we'll see what is happening. The central peak starts increasing in intensity. This keeps coming down. You slowly keep on varying. There's a smooth transition, keeps on going smoothly. Internal lines always keep increasing the intensity. Outer lines starts moving far apart. At the same time, intensity of the outer line starts decreasing. And you will come to a situation when the chemical shift difference between two coupled spins is exactly zero. There is no difference at all. The equivalent spins overlap of the chemical shift, and the J coupling is not reflected in the spectrum. Then you get a single transition. So you can see the transition from AX to AB and to A2. Okay. This is a clear example how AX will become AB. But nevertheless, separation between outer lines of this, any two outer lines, you take this or this, it always gives you J coupling. Irrespective of the strength of coupling, I told you, whether it is strongly coupled to whatever the extent of strong coupling, doesn't matter. But outer two lines, if you take this line or these two lines, this separation always gives JAB, or you can take this which gives you J coupling. J coupling is easy to extract. Only thing is chemical shift you can't get individually, you have to get only difference. Now we go to a next spin system. This is another possibility for two couple spin system. It is called A2. What is A2? The coupling between A and A is zero. There is no coupling at all. I just for the sake of understanding, I have written here A and two this thing. I'll take JAA, JA, or I can call it A1 and A2, doesn't matter. JA, two protons, coupling is zero. And chemical shift is exactly equal. That means they're equivalent spins. So delta delta is zero. Delta delta is zero and coupling is also zero. This is called A2 spin system. This is a very strongly coupled spin system. Remember, AB is strongly coupled. Between AB and A2, it is more strongly coupled spin system. And this is possible only in the homonuclear case. Heteronuclear A2 is impossible because they are different chemical shifts. Entirely their resonating frequencies are different. Proton comes at 500 megahertz, fluorine comes at 470 megahertz. If you take such heteronuclear spins, how can we think of AB or A2? Impossible. So A2 spin system, heteronuclear is impossible. It has to be always homonuclear. Okay, this is the thing. Now, let us try to see how many transitions we get in A2. Remember, you worked out the energy level diagram for AX. I didn't write for AB. Of course, we can also work it out. I leave it to you, to your judgment, to think what to do, and you can work out the energy level diagram. But one thing you have to bear in mind, there is mixed states in AB. It is not pure states. For example, alpha, 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 beta, beta, alpha, beta, beta are the product functions, which are nothing but the wave functions for the weakly coupled spin system. But it is not the same for strongly coupled. It is a mixed state, in which case you have to take into account, instead of pure states, especially alpha, beta, and beta, alpha will turn out to be different like this. You have to take that into account. So you go ahead and practice it. There is the unlimited amount of information available in NMR. We can keep discussing many things. So I did not work out. But A2 I will give you, which is a special case. In the case of A2, again, when you have two spins, this is one possibility, both spins are down, beta beta state. Another possibility, both are up, alpha alpha state. Again, it is a strongly coupled. There is a mixture of states here. You see, the wave functions are not just product functions. You see, this energy state should be written as 1 over square root into beta alpha plus beta 1 alpha 2. Offshore, it should be alpha 1 beta 2. I think there is something wrong here. This mistake is made. So, similarly, this will become negative. This is positive. This is negative. Okay. So, in which case, these two energy states, this is alpha 1 beta 2, beta 1 alpha 2. It should be alpha 1 beta 2 plus beta 1 alpha 2. Similarly, alpha 1 beta 2 minus beta 1 alpha 2. So please read this correctly. This is not beta 1 alpha 2. It is alpha 1 beta 2. Same way here, it is alpha 1 beta 2. This is while preparing the slide, I have made a mistake. I am sorry about it. I'll apologize for that. Please read it carefully. Don't go by what is written here. Listen to what I am telling. This is alpha 1 beta 2. This is alpha 1 beta 2. So these three states are called symmetric states. Okay, these are triplet state. We call it symmetric states here. Whereas this state is anti-symmetric state. What is symmetric state and what is anti-symmetric state? Of course, I don't want to go to details. You read yourself in a little bit of quantum mechanics fundamentals. You will understand. Okay. Now, what are the allowed transitions here? I tell you, this transition is allowed. Okay. Whereas symmetric to anti-symmetric transitions are not allowed. This is a case in A2. A2 has one anti-symmetric transition, which I have written as A0. There are three symmetric transitions, S minus 1, S0 and S1. S1 corresponds to spin state where total magnetic quantum number for this state is 1. For this state, total magnetic quantum number is 0. For this state, the total magnetic quantum number is minus 1. In this case also, total magnetic quantum number for this state is 0. Since it's anti-symmetric state, I wrote it as A0. This is a symmetric state S0, S minus 1 and S1. Now the allowed transitions are only these two, and this is not allowed. And what is the frequency separation of these two? Exactly same. You can find out the frequency separation in this case is exactly same. This is a classic example of a situation. GAA is equal to 0. In the A2 spin system, there can be coupling. Remember, there can be coupling. Still, it is not reflected in the spectrum. I gave you an example of hydrogen molecule. HH coupling is of 276 Hertz. It is present, but you don't see it in the spectrum. That's one case. But it can still be equivalent spin system like A2, but coupling can still be 0. And this is a case where coupling is 0. Now we are getting two transitions which perfectly overlap, exactly overlap, and you are going to get only one peak. And that is what happens. Now I consider a situation where coupling is present. This is also possible, like hydrogen molecule. Now they are chemically equivalent, plus coupling is also present. Again, you write down 4 energy states, 3 symmetric and 1 anti. Again, I made a mistake. It should be alpha and beta 2. This is beta 1 alpha 2. Don't write the same thing again and again. This is a mistake here also, alpha 1 beta 2. Okay. Now, when the coupling is there, very interesting thing happen. All these energy levels are shifted up by J by 4. This is for all the 3 symmetric states in a A2 spin system, the energy level moves up by J by 4. They get destabilized to an extent of J by 4, all of them. What happened to the antisymmetric state? This gets destabilized by a factor of 3J by 4. Now you may ask me a question, how did I arrive at this number, everything? Extensive calculation can be done and it can be shown. But please believe my words, this is what happens. Now, all the 3 symmetric states get destabilized and move up by J by 4, and the antisymmetric state gets stabilized and comes down in energy by minus 3J by 4. All will go up by plus J by 4. Now find out the transitions here. Again, this is a transition. These two are allowed transition, this transition, this transition. Identical frequency again, because energy separation has not changed, because all of them have moved up by same amount. Compared to previous example, you remember the previous example here, they have the same energy separation, same frequency you are going to get, so it will overlap. Here also, but same, because all the 3 energy states have destabilized by the same amount, moved by only J by 4, all of them equally. So the frequency, there is no difference in the frequency. Again, both the transitions are having identical frequencies and they overlap. Yet again, symmetric to antisymmetric transitions are not allowed in this case also. So what does it mean? Here also, you are going to get only single peak, okay, which are overlap. 2 peaks are there which are overlap and you get single peak. So what is the conclusion? In the A2 spin system, whether you have a J coupling or there is no J coupling, does not matter. You always get a single peak. Though there are 2 frequencies, they overlap and give rise to single frequency. You see the difference? If you go to AEX spin system, I got 4 lines. If my general equation, number of transitions allowed, 2nc n minus 1. When 2 spins are coupled, we should get 4 peaks. We got 4 for AX, 4 for AB, but in the A2, even though there are 2 spins coupled, I am showing only 2 transitions. What happened to the remaining 2? This is a special case, that's why I showed you. In this case, there is an antisymmetric state, and symmetric to antisymmetric state transitions are not allowed. As a consequence, A2 spin system always gives 2 peaks. of equal frequency, they overlap, and the resultant spectrum will be a single frequency, single peak. Okay, this is important thing. And this is a classical example of a A2 spin system. Look at this. Say, 1, 2, 3, 4, 1, 2, 4, 5. Tetra substituted benzene. This is identical tetra 1, 2, 4, 5 tetrachlorobenzene. Now this proton and this proton are chemically equivalent. And you will not see J coupling at all. It is a perfect example of an A2 spin system. In this spectrum, you take in any spectrometer for that matter, it will remain A2 only. Okay, it will not become AB or AX at any spectrometer. It always remains A2 because there are only two protons. In this case, both are chemically equivalent and gives it a single peak. Now the question comes, what happened to the coupling here? Is there is J coupling? Of course, there is a J coupling here. Meta coupling is of the order of 0.5 to 1 hertz. It is there. It is a classic example I showed you for A2 spin system. All the three symmetric states are destabilized, moves by J by 4. Antisymmetric state gets stabilized, comes down by minus 3J power. There is a decrease in the energy for this, minus 3J by 4. That is the situation here. There is a coupling. Nevertheless, all the two transitions allowed between symmetric states will overlap and give a single frequency. Another example, classic example for this. This also is a case where A2 with a J coupling present. Okay. So what is the information you get? No J coupling information, only A2 spin system gives a chemical sheet. Measure the frequency position of this. You will say what is the chemical sheet of this. That's all. No other information you can derive in this case. Okay. Now I will go to another example of three coupled spin system. One or two simple examples I'll show you so that we can quickly wind up this topic. Otherwise, there you can go on and on and on and on. Talk about this coupled spin system, 3 spin, 4 spin. In 3 spin, there are n number of possibilities. Each of them can be analyzed, worked out, and see this type of spectrum, everything. If 3 spin, we have 10 possible spin systems. If I go to 4 spin, I'll give you one example. 33 possible combinations I can think of. And each of them, if I have to find out the energy states, frequencies, and transitions, this is not going to be finished in 1 hour or one day. It is going to be a 1 semester course itself. So we will not go more details. I'll give you one weakly coupled spin system and one or two simple example of 3 coupled. This is just you always come across in your day-to-day analysis of the spectra. That's why I'll give simple example. 3 coupled spin system are like this. There is proton 1, proton 2, and proton 3. There is a coupling between these two, 1, 2, 1, 3, and 2, 3. So, as I said, there are n coupled spin system. We have n chemical shifts. N into n minus 1 by 2, that is 3 into 3 minus 1 by 2. There are only 3 couplings. And 2nCn minus 1 transitions will be possible. So, maximum 15 transitions, from which you can get 3 chemical shifts and 3 coupling constants. That's all you will get from that. But the spectrum pattern varies depending upon the spin system, depending upon the chemical shift equivalence and couplings are present or not. We'll take simple example like this. See, these are the possible combinations you can think of. All can be chemically equivalent. Like A2 spin system, I took example. All of them can have same chemical shift and the coupling constant can be 0. Or maybe there and it may not be visible in the spectrum. I won't say 0. It may be 0 or non-zero, but it is not reflected in the spectrum. This is a classic example of A3. We can have A2B or AB2, A prime B or ABB prime, A prime X or AXX prime. In this case, A2B, 2 are chemically equivalent like A2 strongly coupled, and these two together have the same chemical shift and strongly coupled, can have a coupling with another proton. Again, it can be a strong coupling. You understand? 2 spins, like similar A2 what we observed, this can together couple to another proton with a strong coupling effect. It can have a strong coupling. So here you consider the situation. A prime B. A prime means they're chemically equivalent, but the coupling is visible in the spectrum. Here coupling is invisible in the spectrum. Here coupling is seen in the spectrum. And these two together individually can have coupling with another spin with a strong coupling. This can interact with this can interact with this, and their chemical shift separation is much smaller compared to J coupling. As a consequence, this is a very strongly coupled spin system. Okay, you understand that. Similarly, on the other hand, these two can be chemically equivalent with the J coupling observed in the spectrum, but these individually can have a weak coupling with another spin. It is called A prime X. Or these two can be chemically equivalent like A2. Coupling is invisible in the spectrum, but together it can have a coupling, weak coupling with another proton. It is A2X. Similarly, all the three can be strongly coupled. All the three couplings can be visible in the spectrum, in which case it is ABC or ABX. AMX is a weakly coupled spin system. So varieties of combinations here, just for three spins. See how many types, and each of them, if I start discussing, we have individual type of spectrum. Okay, we'll start with AMX. Why I took AMX? Very simple example. Because these are weakly coupled spin system. I told you, look at the letters I have written. A to M, far away letter, M to X, far away letter. The letter I have written AMX clearly tells me these are weakly coupled spin system. So this coupling between A and M is JAM, this is JAX, this is MX. So three couplings and three chemical ships are there. Let us see what we are going to see. This I already explained to you when I explained the number of allowed transitions in three spin case, in the weakly coupled case. We know what is the total magnetic moment of this energy state and these three energy states and these three and these. This is minus 3 by 2 because all these spins are oriented anti-parallel to the magnetic field. Here all the magnetic moments are in the direction of the field. It is 3 by 2. Here 2 up, 1 down, same energy for all the three states. Here 2 down and 1 up, same energy state for all the three energies for all the three states. But minus 3 by 2, half, minus half 3 by 2. Now allowed transitions are between to this, this to this, this to this, and this to this. All are allowed. Now, based on this, we have worked out, and we last time we saw how many transitions are possible: 4 for X, 4 for M, and 4 for A. All those things we observed. I don't want to go into the details clearly. Now I have been showing you these are the allowed transition because change in the magnetic quantum number between two energy states is only 1. So this is why we got 12 transitions. These are the 12 transitions which can be worked out. This is the wave function is nothing but a product function. Always in the weakly coupled spin system, wave function is just a product function. Alpha, alpha, alpha you have to take. But in the strongly coupled case, you know, in the case of AB and A2, AB I didn't write product function, wave function, but in the A2 I wrote. It is alpha beta plus beta alpha by root 2, alpha beta minus beta alpha by root 2. So we have two different mixed states are there. Energy states are getting mixed up. Wave functions are mixed there. But here it is a pure function. Product functions are nothing but the wave function. Again, go to the quantum mechanical analysis, get the frequencies of each of the transitions or eigenvalues first, and then differences of the eigenvalues you find out, and you get the frequencies of the transitions. And all the 12, if you like we saw in the diagram, which correspond to X, which correspond to M, which correspond to A, you can identify 12 possible transitions are possible here. For example, 3 by 2 to half, this is allowed transition 1 to 2. If you look at what is 1 to 2 allowed, it is the X transition. Whereas this and when I take the difference, nu A, nu M get cancelled out. It is the X transition. Like that, you can identify what are the X transitions, M transitions, and A transition. You will definitely get 12 peaks here. Okay. So I have not worked out, but please remember this is very important. Don't forget this. Now it is already there, done here. State 1, 4 to 1 transition, A, 2 to 1. You go back to that table, find out this depending upon which are the energy state you consider. And for transition is going from, let's say, 3 to 1. Take an example here, 3 to 1. 3 to 1 is, if you take the difference, this gets cancelled out, this gets cancelled, it's the M transition. True. What is 3 to 1? Is the M transition. See? And then you can also get from this part, what is written in this bracket, what are the contributions of J. In this case, when you are observing M, you get AM and MS coupling. True, it has to be, right? When A is the active spin, you always get the coupling between active and passive spins. That's what I said. So when A, you are observing M, you get AM and MS coupling. True. And there are 4 peaks. 2 peaks will move to the right, 2 peaks will move to the right, left, from the center of that, from the center of this, or from the chemical shell position of M. with J by 2 of AM and J by 2 of MX. As a consequence, you can find out which is from the center, which is half of JAM and which is half of JMX. So then totally you will get 4 peaks. If you can measure the separation of that, you can find out JAM and JMX very easily. Like 4 transitions will give you 2 couplings. So that's okay. And also there are combination transition. I said all the 3 can go simultaneously, plus of minus of. This is change in the spin angular momentum. I'm sorry, change in the magnetic quantum number of these 2 energy states is +1 or -1. But all the 3 spins are undergoing transitions. The combination transition 1. This is 2, 3. All the 3 are allowed. So essentially, you get 3 combination transitions. What are you going to get here? Look at this parameter. In the previous case, there were JAX, JMX, half of that, all those things were there. Here, nothing. So the combination transitions will not give you coupling information. It only gives you chemical shifts actually. It only arises at some one difference of the chemical shifts. If you find out 5 to 4 combination transition, it comes at sum of nu M and nu X, and difference from that nu A chemical shift has to be subtracted. In fact, if you know these 3 combination transitions and you have 3 equations, 3 unknowns, you can solve it and get the chemical shift of all the 3 easily. You can find out it exactly matches with what you can get from the 12 peaks. So this is also possible. So combination transitions gives you only chemical shift information. And they are very weak in intensity. Normally in weakly coupled you don't see it. Very rarely it is seen. But in strongly coupled, especially go to ABC, all 15 peaks are seen. Including 3 combinations, all 15 will be seen. So strongly coupled case, these combinations become more intense. These are the points. And this is a hypothetical AMX spin system. What did I say when I took the example of AX? Always weakly coupled spin system, intensities are very well defined. There is no intensity anomaly at all. All peaks are of equal intensity, 1:1:1 ratio. These correspond to one spin. It can be A, this is M, this is X. All are equal intensity. This separation is larger, maybe one coupling is larger, other is smaller. This has 2 couplings. If this is A, you have AX and AM. If this is M, you have AM and MX. If this is X, you have AX and MX coupling. Very easily, you can analyze the spectrum and get coupling information. And center of this multiplex gives you chemical shift, center of this gives you chemical shift, this gives you chemical shift. So AMX chemical shifts are also known. Very easy analysis. Now let us see the splitting pattern of AMX. We'll try to analyze in a simple way. And consider a situation nu A is greater than nu M greater than nu X. All the 3 couplings are positive inside. I know chemical shifts like this. I have considered A, M and X. A is here, M is here and X is here. You know, this is a splitting pattern I get. Why? Nu A spin splits into doublet because of M, because of alpha and beta states of M. So this is, okay, I did not write, but this is a JAM coupling. And further, it also, each line is split into a doublet because of coupling to X. So this is JAX splitting. This is JAM, this is AX. Similarly, M can split into a doublet because of alpha and A, and each line of the doublet further split into a doublet because of X, alpha and beta states of X. So this gives you AX coupling, AM coupling, this gives you MX coupling. Similarly, this gives you X1. X will be split into doublet because of A, this gives you AX coupling, and further split by M due to alpha and beta spin states, and this gives you JMX. Okay, very easily I have written here JAM, JAX, JAM, MX, JAX, JM. So what is that you are observing here? In each of these things, the same information can be obtained twice. That is what I was telling you. Single quantum transition of the spectrum has larger number of frequency transitions, large number of transitions. They contain redundant information. I don't need all the frequencies to analyze and get the spectral information. Look at this one. I get JAM here, JAM here also. I get JAX here, I get JAX here also. I get JAMX here, I get JAMX here also. So you can get this parameter twice, two times you can get it. Okay, the spectrum is easily analyzable, but in fact you don't need to analyze everything. If you analyze this, you get two coupling. If you analyze this, get other coupling, unknown third coupling also. So only for chemical shift you have to use this. Otherwise, from these two you can get almost all the three couplings. Now I asked the question. I was telling you one thing. The spectrum is invariant within a sign of the coupling. Let us say one of the coupling. There are three couplings, AM, AX, and MF. Let us say one of them is negative. I change this sign. Let us see what happened to the spectrum. This is what we know. Just now we worked out. Now I am going to make AM positive, AX positive, only MX is negative. Here is the X, where here MX coupling is there, here MX coupling is there. When I interchange sign, what happens? Earlier I wrote this is alpha and beta state. Now it will become, this will become beta state, this will become alpha state. What does it mean? The transitions get, order of transition get reversed. That's all. Nothing else. No difference you will see this in this spectrum. Okay. And this is a classic example of analysis of an AMX spin system, which is taken from the literature. Look at this is A spin, M spin, and X spin. Very clearly written here. A, M, and X chemical shifts. Chemical shift you don't have to worry. You directly get from the center of the multiplet. Also, look at the condition here. JAM is larger than JAX is larger than MX. Why did I write like that? Look at the molecule. I have been telling you the trans coupling is larger than cis, and this is both of them are larger than geminal coupling. This is precisely what we are seeing here. So at the chemical sheet of A can undergo coupling with M, trans coupling. It's a large coupling. Maybe this peak to this peak you measure, that is one coupling. Or center of this doublet to center of this doublet also we can measure, no problem. Then each of this, initially it will be like this, a doublet. Each end of this doublet is further split because of coupling of A with X also. It's a vicinal coupling. That is also quite large. That is why this a large coupling is trans, and this coupling is quite large also, but less than trans. This is a cis coupling. Both are vicinal coupling. Come to M now. At M, you can experience only one large trans coupling and small geminal coupling. So this large separation between this transition to this, or this to this, or from center of this doublet to center of this doublet, if you measure, that pertains to trans coupling. But what about this one? This corresponds to geminal coupling, which is much smaller. So while measuring the frequency J couplings, remember you can measure from this peak to this peak, this to this, it is same, or from center of this doublet to center of this doublet, it is same. Always this gives you trans coupling. And each line of this doublet is further split into geminal coupling into two lines because of this. That's why you get small doublets. If you measure this, you get geminal coupling. This is what it is. Now what about the X? X can have one vicinal coupling. This is of this order. And then in addition to that, it has a geminal coupling. That's why from this to this, if you measure, that is a geminal coupling, or this to this, or from center of this doublet to center of this doublet, you measure, it is a vicinal coupling, and each doublet is split into doublet because of geminal coupling with M. And this is what is JX. I'm sorry. And you will get this one with MX. Okay. So one can also get the similar information from other separation of splitting like this. Here I took this separation and I took this as the JX. Similarly, you can look at this one. You can go back and now use other one. This one I can use this one like this. So you can get the similar information from separation of other separation of splitting. That's why the redundant information contained within all this spectrum. Now AMX in a realistic situation is like this. You see, this is one part A, M, and F. This is AMX spin system. Look at it. But do you call it a real AMX? No. Look at it. There is intensities are not exactly equal. They should be equal intensity, 1:1:1 ratio. They are not. So I would say it is close to AMX, but there is a minute ABC character present here. It is not a perfect weakly coupled spin system. Get the point? So you should understand before. This is a classic example of a AMX. It is through a 600 megahertz spectrum of 2-fluoroic acid. If you take it, look at this one, A, M and X, all lines are equal intensity, very well separated. If you expand this, you will get 4 lines. Expand this, you will get 4 lines. Here you get 4 lines. This center gives you a chemical shift of 1, A, M and X. And if you analyze, like I showed in the previous case, you get J coupling. You see, expansion is here, A part, M part, and X part. And the couplings have been measured very clearly. See, coupling is much, much smaller compared to chemical shift separation. You see, quite larger here. Okay. And this is an AMX spin system of this molecule. 3 protons are present, but you can see there is a minute ABC character also. But nevertheless, analysis is possible. It is a true AMX spin system. This is also classic heteronuclear, not I would say heteronuclear, nuclear other than proton. This molecule has 3 fluorines. All the 3 fluorines are coupled. Again, ortho, meta, para. I'm sorry. See, vicinal, trans, vicinal, cis, and geminal are different. As a consequence, these 3 are well separated, well isolated chemical shifts are there, and they form AMX. Nevertheless, there is a minute ABC character. But you can go to very high field. This is almost at 100 megahertz, I think, or 80 megahertz. This one. But if you go to 400 megahertz and take this spectrum, perfectly we get all lines of equal intensity. Okay. So this is what it is. AMX, you will become A2 when you go to higher frequency. Okay, now I will stop here because another spin system like ABX and another 2 spin system I will explain to you, and then we will go to analysis of the proton spectrum later.